In this section, we're going to discuss ideas that should be familiar. Concepts like linear independence and basis and dimension. We discussed these when we were discussing traditional vector spaces. When we talk about them in this context, we'll be talking about them in terms of abstract vector spaces, but the definitions and the theorems are going to be unchanged. Okay, so the definitions we will give, you'll notice that they will seem exactly like like you already understand them to be. The theorems we will leave unproved because the proofs are exactly the same as they were before. Okay, because the proofs depend on the vector space properties, not the particular kind of vector space. Okay, so the first definition we're going to review is linear independence. So we're going to assume V is a vector space. We're going to take a set of vectors from V. We say that the set of vectors from V, that this set of vectors is linearly independent if and if the only solution to this linear combination equation, the only set of coefficients that solve this homogeneous linear combination equation, is the trivial solution where all the coefficients are 0. Okay? So that's when we say that the vectors are linearly independent. A linearly dependent set of vectors has the trivial solution still. Obviously, setting all these coefficients equal to 0 will make sure that the sum of these vectors will be 0, right? Will be the 0 vector. But if there's also some non-trivial solution, some choice that we could make for the coefficients that aren't all 0, that's when we say the vectors are linearly dependent. Okay? We've talked previously about linearly independent vectors, linearly dependent vectors. Remember some other ideas for linearly dependent vectors, some equivalent ideas, is that there is a redundant vector. So that we can express one vector as a linear combination of the other vectors. And vectors are linearly independent, that means there's not that redundant vector. Okay. By the way, that's the why we use the words independent and dependent. Okay. Independent means that the vectors are totally independent from each other. I cannot replace one of the vectors with a linear combination of the other vectors. Linearly dependent, there is at least one vector that depends in some way on the other vectors. We can express that redundant vector as a linear combination of the others. And so get rid of it without changing the span of the set of vectors. Okay? So now that we have linear independence out of the way, let's talk about basis. So let's let V be a vector space again. Let's set B of vectors of our vector space V is called a basis of V if we have two properties. That the span of those vectors spans the whole vector space, and the vectors are linearly independent. Okay, if those two properties hold, then the vectors form a basis for the vector space. All right, we have some important properties of bases. So first, let's let V be a vector space. Let's let set B be a basis for vector space V. Then every element in V has a unique representation as a linear combination of the elements of V. So just very briefly describing what that means. If vector V is in vector space V, because B, the vectors in B span the vector space, I can express this vector as a linear combination of these vectors. Right, so a1 v1 plus a2 v2 and so on. Okay, we know that's true. What this is saying is not only can we do that, but the representation is unique, which means there's only one choice for the coefficients a1, a2 to an that we can make to make this linear combination true. Okay, if the vectors were not linearly independent, then there would generally be multiple choices, or there could be multiple choices for my coefficients to make the equation true. Okay, what's more, if I have two different bases for a vector space, then there's the same number of vectors in those bases. So let's let V be a vector space. Suppose B is a basis with vectors v1, v2 all the way to vt. Okay, so there are t vectors. That's how many there are, right? And C is a basis for V also, with vectors w1, w2 all the way to ws. So we could see there are s vectors in this set. The theorem says that the number of vectors in the two different bases must be the same. S must equal T. Okay? This is another idea that we've already discussed previously when we discussed bases for traditional vector spaces. We've proved it. The proof is exactly the same as in that previous case. Because the vector space properties still hold. Okay, as long as those vector space properties hold, this theorem holds. And let's add one more definition. Let's let V be a subspace of vector space W. The dimension of V is the number of elements in any basis of V. So for any vector space, the dimension of the vector space is defined to be the number of elements in any basis.